Now let's look at the 2024 AIME II Problem 9. This problem says that we are given 25 identical black chips and 25 identical white chips, and we want to put them to a 5x5 grid. So there are only 25 cells. We can't put 50 chips to a 25 grid, right? So here are the requirement of the feasible configuration. So it says that every cell contains at most one chip. So we can put at most 25 out of 50 chips to the board. And the second condition is that all chips in the same row and all chips in the same column must have the same color. Okay. So suppose let's consider, say, column 3. So for column 3, we know we have 5 cells, right? Suppose one cell is occupied by a white chip. Then what about the other 4 cells? So the bottom line is we can't have any black chip, right? But we can put as many white chips as we like to those 4 cells. Maybe all of those 4 cells are empty, or maybe all of them are occupied with white chips. So either is okay, as long as we don't put a black chip there. So that's the second condition. The third condition says that suppose now we have the configuration that satisfies the first 2 conditions, okay? And you try to add any additional chip to the grid, then that will violate either of the first 2 conditions. Okay. So, for instance, what kind of operation is feasible? Let's imagine the following extreme case. Say for the current grid, we only put 1 chip to the grid, and the other 24 cells are empty. Say the 1 chip that we placed in the grid is white. So we know that it doesn't violate the first 2 conditions, and we can keep on putting more white chips to the board, and that still make all conditions to hold, right? So basically, that is what the third condition tries to say. So this problem asks us to find the number of configurations. Because we observe there are 2 colors of chips, right? And there are lots of the restrictions about making the colors to be identical for every column, for every row. So it motivates me to do the casework analysis in terms of whether for our given configuration, it consists of purely a single color chips, or the board is filled with both colors of chips. Okay. For the single color case, for example, suppose enter some configurations. Say some cells are occupied by white chips, and because there's a single color, so all other cells must be left empty, right? So let's check whether it satisfies all 3 conditions. Suppose we put just 10 white chips on the board. So the first 2 conditions are satisfied. What about the third one? No, because if we have 10 white chips, so we can still add 15 more white chips to occupy those empty cells. And that will not violate the first 2 conditions. So which means that the final solution in this case is the board is entirely occupied by 25 same color chips. So either the board is entirely white or is entirely black. Therefore, the number of solutions in this case is 2. Next, let's look at the second case that the board is occupied with both colors, which means that in the final solution, in the final configuration, so we must have at least 1 white chip and at least 1 black chip. So in this case, let's compute the number of feasible configurations. Okay. So I observed the following fact. So first, because we must have at least 1 white chip, right? So think about it. For any white chip on the board, it has two coordinates, x coordinate and a y coordinate. So x coordinate determines its column, and the y coordinate determines its row. For instance, suppose we have one white chip who has coordinate 3 and 2. So it means that all cells in column 3 must be either empty or white. And all cells in row 2 must be either empty. So some cells in row 2 should be empty or white, right? So basically it tells us that, so for each color, so we must have at least one column and one row occupied with this color. So this is true for both white and black. Okay, so this leads us to the second observation. Let's say white. So how many columns can be occupied by white chips? We know its number is at least 1. But since the number of columns occupied by black is also at least 1, and the total number of columns is 5, so it tells us that the number of columns occupied by white cannot be more than 4. Okay? So analogously, we know the number of rows occupied by white chips also is between 1 and 4. And also, this is the same range for the black chips, the same thing. Okay? So this is the second observation. And then let's look at whether we have any other properties. So now let's say that column 3 and row 4 must be white. Okay. Well, maybe we can add a few more. Say column 3 and 4, rows 4 and 3, 3, 4, 5. Okay, are all white. Then I claim the following thing. Okay, so let me write it down mathematically. Suppose that the columns that should be white are, say, C1 up to Cn, and the rows that are white are R1 up to Rn. Then I'm claiming that every cell xy such that x is the set from C1 up to Cn, and y is from the set R1 up to Rn. This must be white. So which means that in this illustrating diagram, this yellow colored cells must be white. Why? So let's consider any yellow cell. First, can it be black? No. If it is black, it violates the second condition, right? Second, can it be empty? If it's empty, it violates the third condition. When we replace the empty cell with the white chip, so it's still valid, right? So therefore, it implies that so the entire region should be occupied by the white chips. Okay, so once we know which columns and rows are occupied by white chips, then basically for this rectangle, so it should be fully occupied by white chips. And next, let's look at this region. Okay, so what are the features of this region? All right, mathematically says the following thing. So for simplicity, let me denote the set of columns occupied by white to be big C, and the collection of rows occupied by white to be big R. So for any coordinate xy such that suppose x is in C and y is not in R, or x is not in C but y is in R. So that corresponds to the blue region, right? I'm saying that the entire blue region must be empty. Why? Just think about the following thing. let's look at the top left corner blue cell. Suppose we put a white chip there, what happens? You put a white chip, then basically it creates one more column for white chips. But as I said above, so the inner configuration, right? So we already have fixed the which columns are occupied by white. So this is a change. It's not good. Can we make it black? No. You put black, we can see that the first row contains both black and white chips. This is the violation of the second condition. Therefore, the entire blue region must be white. Okay? All right. What about the remaining regions? So we can see that the remaining regions corresponds to columns 1, 2, 5, and rows 1 and 2. Then for the remaining columns and the rows, I'm claiming that they must be occupied by the other color chips, by black chips. Why? They must be occupied by black chips. Okay, so here's the reason. Why? First, they cannot be occupied by white, right? Because it violates the condition about which rows and columns are occupied by white. But why we can't make them to be empty? For instance, let's look at the bottom left. Why can we cannot just make it to be empty? It's because it will violate condition 3, right? Because we put the bottom left one to be black, it doesn't violate the first and second conditions. Okay, so basically we can't have any column or any row that is empty, that is not occupied by anything. That is not good. Okay, so now we have a clear sense about how we make the counting. So basically now we just need to determine that which columns are occupied by white, then the remaining columns are occupied by black, and which columns are occupied, which rows are occupied by white, the remaining rows are occupied by black. So once we know the set of columns and rows occupied by each of these two colors, as I said above, right? So we have the unique configuration about how to put the two color chips to the board. So now we are ready to count. So let me use notation N to denote the number of columns that are occupied by white chips. So it's from 1 up to 4. Let me use M to denote the number of the rows occupied by white chips. This is from 1 to 4. And given N and M. So because we have 5 columns, so 5 choose N times 5 choose M. Okay. So we can do the summation of the binomial numbers separately. And for each summation, coming from the binomial theorem is equal to 2 to the power 5 minus the case that n is equal to 0 and is equal to 5. So minus 1 square. So it's 30 square is 900. So this is the number of configurations for the second case that the board consists of both white and black chips. Recall from the first case that we have 2 solutions when the board just has a single color. So by putting 2 cases together, the total number of configurations is 902.